So, hello everyone. Sorry. Now let's begin our working group meeting. So, welcome to the ITF Savnet working group. It's a pity that my co-chair Joe cannot attend this meeting because of the recent surgery. So we have discussed the content that we will discuss. We will present at this meeting. So let's continue the the meeting. Sorry. So first is note well. This is just a reminder for the ITF policy, especially the patent disclosure uh, uh, and the code of conduct. The most important point is by participating in the ITF, you agree to follow the ITF process and policies. And if you are aware of any contribution is related to your patent or patent application, you should disclose it, especially when the working group document adoption. Uh, and as a reminder, all the activity, ITF activity uh, will be recorded and maybe made public, and the personal information you provide to the ITF will be handled in accordance with the ITF policy statement. And mm, as a participant or attendee, you agree to work respectively with other participants. Uh, okay. Uh, so here is the W working group status of our working group. Currently, we have the two working document for the intra-domain and inter-domain problem segment. I think after the adoption of the two document, we have all known the problem and exist in the intra-domain and the inter-domain. So if you are not familiar with you can reference these two documents. I think this two document is the initial point for our working group. And currently there are other related internet draft uh, focus on the architecture and the solution uh, for the interdomain and intra-domain. And there are also some general component, for example, the seven table structure and some solution component proposal, and also the management document. Mm. So for the goal of this meeting, we will focus firstly the introduction and the discussion of the update architecture document. Uh, so after we finish this document, we can discuss it in detail for the related solutions. And among them, there are some general components, for example, seven table and some information for the current cell measurement information can shared with us. Um, and we will also discuss the various solutions proposed for the intra-domain and inter-domain. So here is the draft agenda for this meeting. First, we will focus on the architecture and related document, and then we will focus on the discussion for the solution related document. And if time permitted, we can there is another additional document will be present. So that's all for this meeting. Is there any questions? Okay, so if there is no other question for the chair slide, then we will begin the first topic for the intra-domain architecture.
Thank you.
我这个切换过来到这个这样可以，现在可以吗？对，它这个鼠标不能离开那个。
Okay. Hello everyone. I'm Lan Cheng from Tsinghua University. I'm going to introduce the updates in Intra-domain Savnet architecture. Intra-domain Savnet architecture aims to achieve accurate Sav in an intra-domain network by an automatic way. It aims to address the problems of existing intra-domain Sav mechanisms and meet the requirements proposed in the intra-domain problem statement draft. Here list the historical versions. We first presented this document in Ietf 115, and in the past few Ietf, we received some comments, and then we updated this document accordingly. And the latest version of this draft is version 07. Let's have a quick review of version 05, which was presented in last IETF. In version 05, we introduced intra-domain cell architecture. Specifically, when we introduce cell-related information, including cell-specific information and local route information, we describe the content in cell-specific information and explain why cell-specific information can generate more accurate cell rules than local route information. We also introduced two rules of Savnet routers and cell-specific information communication mechanism and the self-rule generation procedures. We then use two use cases to illustrate that intra-domain Savnet can achieve more accurate and more efficient Sav than existing Sav mechanisms. And then we finally describe how intra-domain Savnet can meet the 5 design requirements proposed in the problem statement. And in last ITF meeting, we received several comments on version 05. These comments can be divided into two main categories. The one is about architecture improvements, and the other one is about improper or ambiguous words. For architecture improvements, some tells us we should use a figure to overview the overall architecture by displaying sub-information flow in an intra-domain network. And data plane considerations should be added in the architecture. And for improper or ambiguous words, some tells us the description of communication channel and sub-specific information communication mechanism, and some terms like subnet, edge router, and border router can be ambiguous. So we responded to these comments on the Savnet meaning list after IETF 118. We clarify the description of communication channel in the meaning list, and we finally decided to remove this terminology to avoid misunderstanding and refine the related description. We also agree to add high-level data plane considerations in the updated version and cite the draft of Savtable. Before we update this document, we first invite comments on the planned updates on Savnet meeting list. And then we revise this draft accordingly. Here list the main updates in the latest version compared to version 05. In introduction section, we clarify that cell-specific information helps generate more accurate cell rules than using local route information in FIB or RIB. And in terminology section, we add the definition of host-facing router, customer-facing router, and AS border router to replace that ambiguous words such like edge router and border router. In intra-domain Savnet architecture section, we first add a figure to overview the intra-domain Savnet architecture in an intra-domain network, and remove the term of communication channel and clarify the self-specific information communication mechanisms. We also revise figure 3 to introduce the process of sub-rule generation for different routers in intra-domain Savnet, and then add high-level data plane considerations about intra-domain subnet. We also update the use cases section to illustrate that intra-domain subnet can achieve more accurate and more efficient solve on host-facing router, customer-facing router, and AS border router. So we first gave the definition of the three kinds of routers. Host-facing router is an intra-domain router, which is connected to a host network. And customer-facing router is an intra-domain router, which is connected to an intra-domain customer network, which also runs routing protocol. And AS border router is an intra-domain router, which is connected to other ASs. And then we add a figure to overview intra-domain subnet architecture in the updated version before we introduce the details of intra-domain subnet architecture. We first gave the sub-goals for different routers. Host-facing router should generate sub-rules on interfaces facing the host network and block data packets received at those interfaces with source addresses not belonging to the host network. And customer-facing router should generate sub-rules on interfaces facing the customer network and block data packets received at those interfaces with source addresses not belonging to the customer network. AS border router should generate sub-rules on interfaces facing another AS and block data packets received at those interfaces with source addresses belonging to the local AS. To meet the sub-goals, intra-domain subnet requires routers to automatically exchange their sub-specific information. And each router can choose to provide its sub-specific information to any router in the intra-domain network. And then routers can generate more accurate sub-rules by using sub-specific information provided by other routers and its own sub-specific information and routing information in the local fib or rib, if necessary. So here shows two examples. For example, in this figure, router B can identify all prefixes belonging to the customer network by using its own sub-specific information and the sub-specific information received from router A. And then it can perform accurate sub-filtering at the interfaces facing the customer network. And for router D or router E, it can identify all prefixes belonging to the AS by using sub-specific information provided by router A, router B, and router C, and then achieve accurate sub-filtering at interfaces facing another AS. Therefore, a sub-specific information communication mechanism should be designed to propagate sub-specific information between routers. And this mechanism must support automatic update and session authentication for convergence and security requirements. And in the updated version, we clarify that this mechanism can be either a new protocol or an extension to an existing protocol. So how to design a communication mechanism is open to all solutions. We also update this figure to show the workflow of sub-rule generation for different kinds of routers. In this figure, the subnet agent in intra-domain subnet router can use sub-specific information provided by other routers and sub-specific information of the local router and routing information in its local fib or rib to generate sub-rules. And we clarify that routers should preferentially use sub-specific information to generate sub-rules because it can help generate more accurate sub-rules to avoid improper block and reduce improper permit. And if some sub-specific information is unavailable in the incremental or partial deployment scenario in an intra-domain network, Then local routing information can be used to generate sub-rules. But in this case, we must avoid improper block. For example, we can use some looser rules. And we add some data plane considerations in the updated version. Savnet routers will check source addresses of incoming data packets against its local subrules, and drop those are identified as using spoofed source addresses. And more data plane details can be found in the sub-table drafts. We then revise the use cases in the updated version to show that intra-domain Savnet can achieve automatic updates and accurate validation, while existing intra-domain sub solutions such as ingress filtering or strict URPF may need manual update or have improper block problems. So in summary, this document has been updated from Ietf 1.15, and comments received in the past few Ietf meetings are discussed and addressed through Savnet mailing list. Thank you for your comments that can help us improve this document. By following this architecture, the new intra-domain sub-solution can meet the design requirements proposed in the intra-domain problem statement draft. So in the next step, we'd like to call for working group adoption for this draft. Thanks again for your attention and your comments. Thank you.
So, any questions? So, if there is no other person ask question, so I will ask one question. From the protocol design, I think there may be difference for the role of the router. So you have described that there are several roles for the router, so the host facing and customer facing and border router. But from the protocol perspective, their behavior and their action will be the same.
Yeah. We will clarify the new solution should be general for different routers, right? Yeah, we clarify that in the draft. Yeah.
Okay. So, okay.
Thank you.
Good afternoon, everyone. I'm Libin Liu from Zhongguancun Lab. Today, I will present the draft inter-domain source address validation Savnet architecture. Okay, let's first review the inter-domain Savnet architecture. It aims to provide a comprehensive framework for developing new inter-domain solve mechanisms to address the problems of existing inter-domain solve mechanisms and meet the requirements proposed in the inter-domain Savnet problem statement draft. Here is a summary of the historical versions. We have submitted 8 versions in total and presented the version 00 to version 05 during the Savnet workgroup meetings from Ietf 115 to Ietf 118. After that, we have updated 2 versions according to the comments and feedback during the Ietf 118 Savnet workgroup meetings and the discussions in the mailing list. Today, I will present the version 07. Okay, here is a summary of the comments on version 07. We have grouped them into 3 categories. The first one is is to help improve the presentation of the inter-domain Savnet architecture. Both Zhou and Aijun suggested that the draft should add a new architecture figure displaying the network topology and the communication flow of the cell-related information. Xueyan suggested that the draft should add data plane considerations. And Zhou also suggested that the draft should draw multiple links between neighboring AIs in their figure, including network topology, and states which cell the inter-domain Savnet architecture performs. And the draft should add a paragraph that states how the inter-domain Savnet architecture provides incentive. The second type of comments is about adding more considerations on cell information sources. Anton commented that they can use our data to automatically update the ACL rules, but the problem is that our data is not validated. And both Anton and Aijun paid attention to the trustworthiness of the cell-specific information communicated between AIs. The third type of comments is to help clarify the descriptions of some concepts. Huaimo commented that there are no need of cell-specific communication channel. And Zhou also suggested that a draft should clarify cell-specific information is more accurate, timely, and trustworthy than the other information. Regarding to the first type of comments or response, we have improved the presentation of the inter-domain Savnet architecture. In section 1, we have added a new paragraph to illustrate the incentive of inter-domain Savnet architecture. In section 4, we have added a new architecture figure and added the high-level descriptions about a cell data plane. In sections 4 and 8, in all figures, we have added multiple physical links for neighboring AIs to indicate that inter-domain Savnet performs AIS level cell. We have discussed these updates in the mailing list. Regarding to the second type of comments or response, we have added more considerations about cell information sources. In section 5.1, we have added a new section to discuss our data and included it in the general information for inter-domain cell. Additionally, in the mailing list, both Paul and Michael have discussed their concerns about the availability, accuracy, and slow update of the IR data. In section 7.1, we have added a requirement that a Savnet agent should validate the authenticity of the connection for communicating the cell-specific information to verify whether the cell-specific information is provided over a secure connection with an authenticated AS. We have discussed automatic ACL rule updates using our data and the validation requirement of cell-specific information in the mailing list. Our response 3, we have clarified the concepts of information channels and the cell-related information. In section 1, we have summarized the accuracy, timeliness, and the trustworthiness of cell-specific information. We have added a new section 5 to illustrate the cell-related information and distinguish them. In section 7.1, we have removed the cell-specific information channel and described the cell-specific information communication mechanism. Also, we have discussed the cell-specific information and its corresponding communication mechanism in the mailing list. Okay, let me summarize the main updates of version 07 compared to version 05. We have revised the introduction section. In this section, we have summarized the cell-specific information and general information and their differences, and have explained the incentive of the inter-domain Savnet architecture, and summarized the accuracy, timeliness, and trustworthiness of cell-specific information. We also removed the descriptions for communication mechanism for cell-specific information in the design goals section and moved this to the section 7.1. We have revised the inter-domain Savnet architecture overview section. In this section, we have added a new inter-domain Savnet architecture figure and its relative descriptions about the architecture. And we have added the high-level data plane considerations as well. We have added a new cell-related information section and revised the cell information base, Savnet communication mechanism, and the use cases sections accordingly. Okay, all these updates have been discussed and illustrated in the mailing list of Savnet work group. Let's overview the inter-domain Savnet architecture figure. The architecture figure displays an AS-level topology and the communication flows of all the cell-related information. Here, we use ASX as a representative to describe the AS-level topology and illustrate what cell-related information the Savnet agent within ASX will collect and where the information is from. Here, the topology figure shows all peer ASs of ASX, including its customers, providers, and later peers. The arrows in the figure shows the directions of all cell-related information. Based on the cell-related information, the Savnet agent within ASX can generate cell rules and perform AS-level inter-domain cell. ASX has deployed the Savnet agent, and it can obtain the cell-specific information from its customer AS, which also deploys the Savnet agent. And it can obtain the local routing information from the BGP update messages of its peer ASs. And it can also obtain the RPKI, ROA, and ASPA objects from the RPKI cache server and the RR data from RR database. Okay, in Ietf 118, we have illustrated the cell-related information, which includes the general information and cell-specific information. General information currently consists of IR data, local routing information, and RPKI ROA objects and ASPA objects. In the general information, reliable IR data can augment the cell table, but IR data may not be accurate, and they are not updated in a timely manner. Cell based on the local routing information, such as URPF-based mechanisms, may lead to improper blocks or improper permits in many scenarios, as analyzed in the inter-domain Savnet problem statement draft. RPKI, ROA objects and ASPA objects are verified and more trustworthy and work better than the two of above information sources in many scenarios. But in some partial deployment scenarios, they may lead to improper blocks or improper permits. They are stable but not updated in a timely manner, and thus may lead to improper blocks when prefix or routes change. Differently, some specific information includes a prefix and their legitimate incoming directions for accurate cell, and can be updated automatically in a timely manner. A Savnet agent validates the authenticity of the connections for communicating the cell-specific information. Inter-domain Savnet architecture proposes the cell-specific information. And based on the analysis, here we conclude the table. Okay, Savnet agent uses cell information base to consolidate cell-related information. The right table shows the cell information base of AS4, which appears in the topology of the left figure. Each row in the SIP records the index, the prefix, and the prefix valid AS level incoming direction, the AS relationship, and the corresponding information source. So based on the cell-related information, how does the inter-domain Savnet utilize them to generate accurate cell rules? Inter-domain Savnet assign priorities to different cell information sources. The left table and recommends that using the information source with a higher priority to generate cell rules. The left table shows the priority rankings for the cell information sources, including cell-specific information and general information. The priority ranking from 1 to 5 represents the high to low priority. In the cell information base of AS4, the prefix P1's incoming directions are different for the cell-specific information and general information. The inter-domain Savnet recommends using the cell-specific information to generate cell rules for prefix P1 here. The site-specific information communication mechanism and the general information communication mechanism and the management mechanism are used to communicate the site-specific information, general information, and the management configurations from operators. The site-specific information communication mechanism can be implemented by extending an existing protocol or a new protocol. If it is implemented by extending an existing protocol, the protocol itself cannot be affected. Here we use a use case to show the incentive of inter-domain Savnet architecture. The two figures show the same scenario, cell at customer interface and the limited propagation of prefix caused by no export. In the two figures, S1 is the customer AS or S2 and S4. S2 is the customer AS or S4. And S5 is the customer AS or S4 and S3. S4 is the customer AS or S3. And the path of the legitimate traffic with source address in P1 and destination address in P4 is S1, S2, and S4. In the scenario where S1 does not deploy the inter-domain Savnet architecture, like the left figure, existing URPF-based cell mechanisms would block the legitimate traffic improperly. But if both AS1 and S4 have deployed the inter-domain Savnet architecture, like the right figure, S1 can communicate the site-specific information, P1, S2, to the S4. S4 will be aware that the traffic with use P1 as the source address can arrive at the interfaces facing S2. Then it can forward it properly. Okay, our summary. New inter-domain cell mechanisms developed following the inter-domain Savnet architecture can meet the requirements proposed in the inter-domain Savnet problem statement draft. And the inter-domain Savnet architecture and its updates have been presented during the Savnet workgroup meetings from Ietf 115 to Ietf 118. And this document addresses all the comments from our community, and it discussed in the mailing list of Savnet workgroup. Okay, thank you very much for the comments and the feedback from our community to help improve this draft. Okay, I think it's time to go move to the next stage. We call for the workgroup adoption for this draft. Thank you very much, and I'm happy to take your questions.
Okay, Ben.
Hi there, Ben Madison from Work Online. Just quiet. So thanks for the presentation. I think I've now raised this at every Savnet meeting, and this solution suffers from the same issue that BarSav does as well in its use of RPKI-based objects, which is that it imports kind of similar but not the same, importantly distinct semantics onto existing RPKI objects that don't exist today. And it has one really, really problematic feature, which is that things get stricter when information goes away. So if there is a failure in the global RPKI system, this mechanism, and this is true of BarSav as well, gets stricter, more traffic gets dropped, filters get tighter. And those are not the semantics of how we use things like ROAs today and how we'll use ASPERs in routing security in the future. Me and people like me have been going around for the last several years evangelizing the use of origin validation. And one of the key arguments that we've used when we've been speaking to other operators is that if there is a systemic failure in the global RPKI system, things fail open, traffic continues to move, filters get looser rather than stricter. And if this was to become widely deployed in its envisaged state, that would change, and it would jeopardize the use of RPKI and routing security in general. It's a really big problem, and it's not one that I've seen anyone make any moves to address. Fundamentally, it needs new signed objects. If we want to use RPKI data for this kind of a use case, we need new signed objects. And I'm happy to help, but up until now, no one's proposing it, and it's a killer. It's an absolute deal breaker.
Thank you.
Serial.
Yes, you can hear me? This is Sri Ram from NIST. So can you go to slide 14 for a moment, please?
14, right?
Yeah, that's correct. Yeah, thank you. So in the left-hand figure, I mean, you're considering URPF, but you're not considering BARSAV. If you did consider BARSAV in this figure, it is possible that that AS4 can learn about the prefixes of AS1 and AS2 using the ASPA information as well as the ROA information. So I just wanted to point that out, that you are selectively comparing it with URPF, but not another existing protocol that is BARSAV. Assuming that you have ASPAs available, and I mean, Ben, I heard Ben's comments, but we'll consider that. But if you were to include BARSAV, then the left-hand figure BARSAV works as well. No?
Yeah. Okay. Pass.
Hi, Shriram, it's Ben here. Was that question directed at me or was it a bit unclear?
We can discuss that separately. I need to understand some of your comments more clearly. The question was addressed to the speaker only regarding the slide 14. On the left-hand side, BARSAV works equally well. URPF maybe doesn't because of the no export, but BARSAV would.
Yeah, I got that point.
Yeah, I agree with that as well. I think BARSAV solves that topology as well.
Thank you.
Okay, clear. 还有问题？
Hey, Kevin Patel Arcus. The other thing, as Ben said, over and above origin validation, does this also cover a man in the middle attack who can generate a prefix inside BGP with the right AS origin, but can hijack the path? And how would you then solve the problem in an AS, receiving AS, which is actually implementing this solution? So do you need forward signing mechanism or ASPA that CyberOps is working on to say that I have to somehow authenticate the series of ASs from where it's transitioning towards, assuming this proposal is not enabled? Yeah.
I think
I can take it on the mailing list, but something for you to think
okay,
about.
okay. Thank you.
So I said what Ben Medicine said was about origin validation. But I'm not sure if this solution even covers the fact that assuming covers the fact that there is an AS in middle that creates a right prefix with a right origin, inserts it into BGP. And how would this solution cover it? BGP-SEC forward signs. So you can do a man in the middle attack. If such a man in a middle attack happens here, how would the receiving AS that is implementing this still provide a right solution?
Yeah. I think it's about the security issues, right? Yeah. Actually, in the architecture draft, we have considered some security requirements for the self-specific communication mechanism. I think it mainly include two types of security threats: session security threats and the content security threats. Maybe we need to validate the contents of the from self-specific information from the origin AS, and also we need to guaranteed that it cannot be modified by malicious as in the intermediate of the path, right? So I think in the draft we have already discussed the security concerns exactly, but for the security design about the solutions, I think we will use a separate draft to solve it. Yeah, thank you.
So just to follow up on the concern that Kay was raising, I think that, I mean, I haven't sat down and thought about it carefully, but I think that the problem that Kay is describing arises when you have less than perfect ASPER coverage of the links in the graph. Because as soon as someone can appear to be downstream of a valid source direction without contradicting anything in the set of published ASPERs, then the attack that Kay is talking about becomes possible. And to be honest, I don't think that we have a way of solving that using out-of-band signaling. I think if we want a solution to that, which is a very, very difficult attack to protect against, we need some sort of in-band signaling. We need some sort of source signing in-band in the packet header, which, I don't know, you can do that if you want, not me.
Thank you. Yes.
Yeah, okay. So I think these two documents is for the architecture, the details solutions will be discussed in a separate document. So we can discuss later.
Okay, hello everyone. I'm Mingxing Liu from Huawei. One of co-authors of the draft, General Source Address Validation Capabilities. At the last meeting, we have introduced existing tools that has many limitations, such as inaccurate validation and high operational overhead. Because their capability are derived from other functions, e.g. FAB and ACL. We summarize the general cell capabilities from intra and inter-domain cell architectures and propose the cell modes. Mode 1 is the source address allow list that takes effects on an interface. The allow list contains all source prefixes that are allow list that are allowed coming into the interface. Source prefixes that are not in the allow list are considered invalid. Mode 2 is the source prefix block list that takes effect on interface. Mode 2 aims to block some invalid source prefix coming into the interface. Source prefixes that are not in the block list are considered valid. Mode 3 is prefix-based interface allow list or block list. Mode 3 is in a router is a global level mode. For given source prefix, the traffic only be allowed coming in through the specific interface list. This slide shows updates. Firstly, we update the application scenario of mode 1 and mode 2. Secondly, we revise the description of mode 3. Mode 3 is the prefix-based interface list. It may be an allow list or a block list. Mode 3 and mode 1 or 2 are not mutually exclusive. They have different application scopes. Mode 1 and mode 2 are exclusive. They have the same application scopes. Lastly, we revise the validation procedure section to make the procedure more general. This figure shows how to apply mode 1 or mode 2 on the interface. Subnet 1 has only one prefix P1. That means the valid packets from subnet 1 has only one source prefix P1. So we can apply a source prefix allow list on interface A to filter out the spoofed traffic from subnet 1. The allow list contains only one prefix p1. Similarly, subnet 2 has the prefix p2 and p3, so we can also apply a source prefix allow list on interface B and C. Because subnet 1 and subnet 2 are connected to only one AS, so the valid packets with these three prefixes as the source prefix do not enter AS1 from ISP network. So we can apply a source prefix block list on interface D to filter out spoofed traffic from ISP network. The block list contains these three prefixes P1, P2, and P3. Mode 3 is a global validation mode, aiming to filter out spoofed packets with forged specific source address, source prefix from all directions on router. Let's consider R1. Subnet 1 is single homed to R1 through interface A and has only one prefix P1. That means the source prefix P1 has only one valid incoming interface on R1. That is interface A. So we can apply a incoming interface allow list for the source prefix P1 on R1 to filter spoofed traffic from other directions. Let's consider R3. Obviously, the packet with P1 as source, the valid packets with P1 as the source prefix cannot arrive at R3 through interface C and D. So we can apply an incoming interface block list on R3. The block list contains interface C and D. Let's consider AS2. AS2 is multi-homed to multiple AS. It can arrive at R3 from any interface. That depends on inter-domain dynamic routing. So we can also apply interface block list, valid incoming interface block list on R3 for prefix P2, but it depends on specific cell protocol and the inter-domain dynamic routing. This slide shows the validation procedure. When receiving a packet, the router will take the source address and the incoming interface of the packet as the input and look up the sub rows to get the validity state. Firstly, the packet is validated by the enabled interface scale mode, i.e. mode 1 or mode 2 to get the validity state 1 and or validity state 2. If the validity state 1 or validity state 2 is invalid, the final validity state is invalid, and the packet does not have to be validated by mode 3. If the validity state 1 or validity state 2 is valid, the packet still needs to be validated by the enabled mode 3. If mode 3 is not enabled, either the validity state 1 or the validity state 2 is the final validity state. This slide shows the relationships with the intra and inter-domain architecture. The intra and inter-domain architecture drafts focus on sub-framework and some rule acquisition in the control plane, and do not focus on the sub-capability of the data plane. This document focuses on general sub-capabilities of the data plane required by both intra and inter-domain architecture. Also does not address the specific implementation of the data plane. This document summarizes the common points of the intra and inter-domain architecture, which can get the design of the sub-solutions. Many thanks to these guys for their valuable comments. and feedback. So welcome any questions and comments and ask for group adoption. Thank you.
One question. I wondered, do we need the mode 3? I think you can configure the mode 3 in the global manner, but for take effect, it can be changed into the mode 1 and mode 2. So it is necessary to define the mode 3.
Yeah. We consider we think that mode 3 is applicable applicable to the scenario where valid incoming interface or source prefix change dynamically, because the dynamic routing may cause the source prefix block list or allow list to constantly change. So we use mode 3 to suitable for the dynamic routing.
I think we can discuss offline. I think the mode 3 is
okay. We can
not
have a
not the
discussion.
necessary mode.
Okay. Thank you.
Okay.
Hello, everyone. This is Shuai Wang from Zhongguancun Laboratory. Today, I will introduce more methods to measure IP source outbound spoofing on the internet. We have talked about the DNS proxy-based method in Ietf 118. So let's revisit it briefly. For DNS proxy-based method, we use a scanner to send a DNS query to the DNS proxy in the target network. And the DNS proxy will not modify the source IP address and forward the modified DNS request to the DNS resolver. So this is a spoofed packet whose source IP address is client, but not the DNS proxy. So in this way, our scanner will receive a DNS response from the DNS resolver directly. Similarly, the DNS response will not changed by the DNS proxy. However, for a scanner, the structure of the internet is a black box. We cannot figure out what happened in the internet when receiving a DNS response with a source IP address that is different from the destination IP address of the DNS query. Even we could not distinguish between the two mentioned cases. What is worse, when no DNS response is received by the scanner, we do not even know why, what happened in the past. So we improve upon the DNS proxy-based method by using DNS traceroute, so that we can learn about the path of the DNS query from the scanner to the DNS proxy and then to the DNS resolver. We set different time to live values in the same DNS query. There are some advantages of DNS traceroute-based method. First, the source IP address of TTL exceeded messages and their order reflect the path taken by the DNS query. As we mentioned, including both the path from the scanner to the DNS proxy and the path from the DNS proxy to the DNS resolver. So in this way, even if the scanner does not receive a DNS response, we can tell whether the spoofed packet traveled outside the targeted network based on the information about the path. Second, the destination IP address of the DNS query can tell us whether it has been changed, which the destination IP address can be found in the data section of SMP TTL exceeded messages. So if only the destination IP address of a DNS query changes, we know a spoof packet is generated. And we should note that the source IP address of the DNS query is still the scanner, because SMP error messages are sent back to the scanner directly. There are some different results about the DNS trace route. In the case number 1, the scanner receive DNS response, and the spoof packet are generated at the DNS proxy. Look at this real case. We send the DNS query to this target, and we found at the 12th and the 13th hop, the destination IP address is changed to 48, and then the spoof packet are sent to the 48 to the DNS resolver 48. Finally, the DNS resolver sent back a DNS response to our scanner. However, the destination IP address of a DNS query could be changed before reaching the DNS proxy. So if this happens, the scanner will receive the same DNS response as that in this case, in case number 1. So this is the case number 2. The scanner received DNS response, but the DNS query is forwarded before reaching the DNS proxy. This is the case. I cannot see as the 6th hop, the destination IP address is changed. However, we did not find the DNS proxy's IP address appear. So the IP address, the destination IP address is changed before reaching the DNS proxy, and finally, the modified packet are forwarded to the DNS resolver. Further, we found the the target IP address belongs to AS 265.911, but the destination IP address is changed at a preceding node, and this preceding node is belong to the provider AS. We think this may be caused by DNS interception. So in this case, existing DNS proxy-based method will incorrectly determine that the target network allows outbound spoofing. However, in fact, the target network is not mirrored, but another network provider is mirrored. For case number 3, no DNS response is received by the scanner, but the spoof packet reached outside the target network. We can say that the target IP address belongs to this AS, but the last responsive hop belongs to different AS. So we know the spoofed packet has traveled outside the target network. And in case number 4, no response is received by the scanner, but the spoof packet does not reach outside the target network. This is the last responsive hop, and we found that this is the same AS. So we know that the spoof packet was filtered by the target network, because if our scanner send a DNS query to the DNS resolver for ACE directly, we will receive a DNS response. But in this case, we did not receive the response. So with the help of the detailed paths, we can differentiate between case number 3 and case number 4. To conclude, with case number 1 and case number 3, we know that there is no outbound cell deployed in the target network, but for case number 4, there is outbound cell. For case number 2, no outbound cell deployment is unknown. We do not know about this. Finally, we improved upon this method. We use some other kinds of packets behind the DNS to measure outbound spoofing when destination NAT exists in the target network. For example, NTP-based method, with the NTP-based method, we found 14 NTP proxies forwarded to NTP servers in different ASs. And the TCP-based method, we send TCP same packet to the target network, and we found that DNS trace route-based method is more reliable than TCP proxy-based method, and the TCP trace route-based method help us to identify more 348 ASs that allow outbound spoofing. Okay, that's all. Thank you.
So, because the time is limited, so if you have any question, you can put it on the list. I think this draft can be evolved to the future measurement for the deployment of the Savnet mechanism. Okay.
Okay, thank you.
Hello everyone.
Yeah, we can hear you.
Yeah.
So.
Yeah. Hello everyone. I'm Savnet Yue from China Mobile. I will introduce intra-domain south support via IGP and via BGP, and I will introduce intra-domain south support via IGP first.
Sorry. Okay, I will turn the slide as your request. Okay, let's continue.
Next slide, please. Source address validation is important for defending against source address spoofing attacks, such as reflection attack. However, existing mechanisms had their own limitations. ACL-based ingress filtering has no automation, and strict URPF is overly strict, which may lead to packet loss. And the validation under loose URPF is permissive. Our focus is computing Savnet rules based on intra-domain connectivity. Savnet rules can dynamically adjusted to the changes of network topology, apply interface-specific filtering, and prevent improper packet loss. Next slide. IGP process framework is shown in the figure, and the source prefix can be statically configured or distributed within the domain via IGP, and the IGP LSDB will contain the source prefix information and the reachability information. Based the source prefix information and the reachability information in two ways. The Savnet agent utilizes connectivity algorithms to calculate the source port information of the source prefix and generates the cell row table. And during the connectivity calculation, it is required to perform two-way neighbor check for validation. Next slide. The main idea of the connectivity calculation is that traverse all interfaces of the Savnet-enabled node, and for each interface, perform BFS algorithm to traverse all neighboring nodes to get prefix and generate Savnet row entries. And finally, we merge the Savnet row entries according to the prefix. Next slide. For example, Savnet row in scenario 1, we traverse interface A1 and A2. And for interface A1, we can get P1 and P2 according to the reachability. A to B, B1 to C, and B2 to D in BGP LSB of node A. Therefore, we can generate the several entries P1A1 and P2A1. And then for interface A2, we first search the neighboring node E. And from E1, we know the neighboring node of node E, node F, and get the prefix P3 and generate several entries P3, A2. There are similar process of generating several in the other two scenarios. Next slide. In the case of inter-area, internal source prefix is advertised by ABR, and the external prefix is advertised by ASBR. For example, P1 and P2 are advertised by ABR node B. When it traverses to ABR or ASBR node, the nodes can know the prefixes. Next slide. We also provide optical IGP extension with source prefix flag to control the validation range of the concerned source prefixes. For ease, IPv6 Savnet source prefixes are advised using IP extended reach TLV, while IP value Savnet source prefix are advertised using IP value reachability TLV. For OSPF, Savnet source prefixes are advertised using OSPF v2 extended prefix octo LSA, and for OSPF v3, Savnet source prefix are advertising using OSPF v3 extended LLC. Next slide, please. Now, let's introduce another typical scenario where the source prefixes are propagated via IBGP over IGP-based neighbor establishment practical networks. It is common to propagate source prefixes via IBGP, which establish neighbors using the underlying IGP network. All BGP neighbors exchange source prefix information through a route reflector. Next slide, please. So how to generate subroutes in this scenario? We first calculate the subroute 1 via IGP using the process before, which are related to the BGP next hop. And in step 2, we obtain the source prefixes published by the BGP neighbor and fetch the subroute 1 table corresponding to the next hop of the BGP neighbor. Then inherit the source prefixes list from the neighbor's subroute 1 table to generate a BGP subroute table. Next slide. For example, generating subroutes for node A. In step 1, we calculate the intra-domain next hop subroute 1 table through the IGP protocol. Then for A1, we can get a router 5 A1, router 2 A1, and router 3 A1. And in step 2, iterate through the BGP neighbors next hops. If the neighbors has published source prefixes, for example, the router 2 published P1 and router 3 published P2, and we use the next hop to search the next hop row 1 table, and we can search the router 2 and find the interface A1 and router 3 with the interface A2, and inherit the source interfaces and generate the BGP subroute table prefix 1 A1 and the prefix 2 A1. Next slide. We conclude intra-domain solutions. Besides the ACL and the URPF, the reverse SPF calculation may require complex calculations and difficult to calculate backup ingress interface for routers with primary and backup paths. And there are also BGP-based SPA SPD path probing method, and it may require network-wide update, and the path probing-based solution may result in delayed routing convergence. And the method in this draft has simplified computation for quick convergence and can be fully deployed incrementally. Next slide. And in our next step, we will add a multi-home subnet scenario and add restrictions to memorize traversal of interfaces belonging to the same group, ensuring a more accurate determination of the integrous interface. Next slide. Then I will introduce Savnet use cases. Next slide. In mobile transport network, there are optical connections between CSG and edge node, that is between the access network and the aggregation network, which use IP or Ethernet technology. Their common deployment is to use MPLS VPN as overlay technology, and the validation of label packets where MPLS VPN deployments is out of scope of the Savnet. So the only location for Savnet is in access network, but Savvy may be enough. And in cross-domain network between different service protocol, eBGP protocol should support Savnet. Next slide. A typical fixed transport network is also hierarchical and divides into access network, metro area network, and background network. In access network, there are optical connection links between fixed user and broadband network gateway, that is BNG nodes, which use IP or Ethernet technology. And metro area network use IGP for path connection, and maybe use IGP for user traffic, or it also can use BGP for user traffic, and MPLS VPN for service traffic as overlay. And background network use BGP for the path connection. Next slide. So the most feasible way for packet validation is at the location closest to the traffic. For the upstream traffic, is at the BNG, and for the downstream traffic, the best location is at the edge routers of background network. If there is no Savnet, we can use it at the metro area network node. And for the sub function used at BNG for the upstream traffic, the BNG applies the sub function to determine whether the source address of packet belongs to the legitimate user and inbound port. And for the downstream traffic, the BNG first advertises the source route prefix of broadband user to the upstream routers and receive the reachable route from the upstream router. And after receiving the traffic from the receiver, the BNG applies the sub function to check whether the source address of the packet is valid and whether it matches the backed in bound port. The detailed SAO policy and function is out of scope of this document, but their options ways described at the SAO IGP or SAO BGP. Actually, in this use case, we can apply the Savnet policy using path connectivity method via IGP or BGP according to the user route distribution protocol. At BNG, we can use the Savnet method at BNG or the aggregated router of metro area network and the edge routers of the metro area network in the same AS. And next slide. So any questions and comments are welcome.
So I ask one question. In your ITP-based solution, you mentioned you define the source prefix flags. I think where it is necessary for the source prefix flag. If it is not, because you use the existing LSA advertisement for the flooding of the prefix. So if the flag is not necessary, we can use all of the existing mechanism for the IGP or BGP based solution. So can you explain what's the reason to define the source prefix flags?
First, we think it's optional flags to extend IGP. It may used for when we want to control the range of the concerned source prefix. Of course, if we don't need that function, we can don't extend the IGP or the BGP. Yeah. And if we don't extend the protocol, it may more useful for and the simplicity for the employment.
Okay. So for the use case document, I think future you can it is the deployment scenario for the Savnet mechanism. So I think you can consider to merge it into the architecture for the architecture document for the possible deployment scenario. Okay.
Yeah, we can do it in our next step.
I think it will give some guide for the operator to deploy the Savnet mechanism. Okay, let's continue the next presentation.
Okay, thank you.
Hi everyone, I'm Lan Cheng from Tsinghua University. I'm going to introduce a new inter-domain SAV solution called BiconSAV. This solution uses ASPAR and ROAS data to generate SAV filters. So the primary design goal of SAV is avoiding improper block while maintaining directionality. and existing self solutions such as EFP UIPF typically generate ingress allow list filters by using information related to customer coin. However, solely using an allow list may cause legitimate traffic to be blocked if the allow list fails to identify all prefixes belonging to the customer coin. For example, IFC H704 proposes a scenario, and in that scenario, some existing UIPF-based solution may have improper block, such as strict UIPF, feasible UIPF, and EFP UIPF algorithm A. Here we use a similar example to show improper block problem of solely using an allow list. In this figure, there are 5 ASs, and we focus on ingress self-filtering on AS4. And we can see AS1 has 2 provided ASs. They are AS2 and AS3. And AS1 attaches no export to all prefixes announced to AS2. So in this way, AS4 will never receive routes for prefix P1 and P2 from its customer AS2. So in this case, EFP UIPF algorithm A and algorithm B in AS4 will have improper block problems. It will block legitimate data packets received from AS2 with source addresses in prefix P1 or P2. Okay. And to achieve more robust self-filtering upon EFP UIPF, more recent self-solutions such as Basel suggest to additionally use ASPAR or RUA data to generate a more robust self-allow list filter. However, when some ASPARs or RUAs related to the customer coin are missing, for example, in this figure, if AS1 doesn't have ASPAR, existing solution may still have improper blocks. So how to perform more robust ingress self-filtering when some ASs don't have ASPARs or ROAs? In this draft, ByConsole suggests to additionally use a self-block list on an interface facing a customer or lateral peer AS. The block list should contain prefix belonging to the provider coin. The provider coin of an AS is defined as the set of ASs an AS can reach by using only customer to provider links. And then prefixes belonging to the provider coin should not be used as source addresses in data packets received from any customer or lateral peer, according to the value free. And so, ByConsole suggests to use BGP, updates, ASPAR, and ROAS data to generate the block list. Here shows the block list generation procedures, but due to time limits, I will just briefly introduce these procedures. We will firstly use BGP updates and ASPARs to identify as many as ASs in the provider coin, and then we can use BGP update messages and ROAS to identify prefixes belonging to ASs in the provider coin. And then we can use this self-block list filter to perform self-filtering. It will block data packets received from customer or lateral peer ASs with source addresses covered in this block list. And this block list can provide immediate incremental benefits. If the block list doesn't include all prefixes belonging to the provider coin, it can still block smoothing traffic while avoiding improper block when some ASs ASPAR are available. We use an example to show the ingress self-filtering by using block list. In this example, AS6, AS7, and AS8 are belonging to the provider coin of AS4. If AS4 can identify all prefixes in the protocol, it can block data packets received from AS2 or AS5 with source addresses in P6, P7, and P8. But if AS4 only identifies partial prefixes in the protocol, it can still block data packets received from AS2 and AS5 with spoofed source addresses in prefix P6 and P7. And it can avoid improper block. We also provide some practical deployment considerations for BiconSolve. We believe we should use both allow list and block list filters together. So since it's difficult to make sure the allow list can cover all prefixes in the custom code, a self block list is needed. But we found solely using a self block list may also block some legitimate traffic in some CDN or DSR scenario. So we give the recommended self procedures. We should first check if source addresses of data packets received from a customer or lateral peer AS are included in the corresponding allow list. This allow list can be generated by using existing solutions such as EFP, UIPF, or BarSolve. If so, these data packets will be accepted. But if not, we will go to step 2. In step 2, we will then check if source addresses of data packets are included in the corresponding block list. If so, these packets will be blocked. But if not, these packets should be accepted to avoid improper block. Okay, that is my design of the BiconSolve. Welcome. Feedback, welcome. Thank you.
Yeah, Ben.
Hi, Ben from Work Online again. Thanks. I think that's an interesting idea. It still suffers from the issue that I raised earlier about the semantics of signed objects. So
yes.
I won't go back through that. I think that it starts getting. I mean, possibly there's more detail in the draft itself that I haven't read yet. But I think that it gets a lot more complicated than you seem to suggest, where you have a provider cone and a customer cone that aren't disjoint. There's plenty of places on the internet where the same pair of ASs are both customer and provider to one another, possibly in different regions or in different circumstances. And I can imagine scenarios where, for example, you've got one part of the RPKI tree that's issued some set of prefixes for a given AS and another part of the tree which suffers a failure that covers other prefixes. I think there's lots and lots of corner cases here where this ends up in pretty screwy behavior. I think it's an idea that's worth pursuing, but I think you've got to be pretty careful, and I think that you'd need to do a lot of measurement in order to be sure that it's safe.
Okay, thank you.
Syria.
Can you go back a couple of slides? Yeah. So there seems to be, unless I misunderstood something, there seems to be a fundamental flaw in the design. If you look at this picture on the left and remove AS1, so AS1 is not there. So now you have AS5 has AS3 as customer and AS4 as AS2 as customer. It appears to me that your design would include P3 among the allowed. I mean, it's not included in the allow list. So prefix P3 at AS3, again, like forget that there is AS1, remove AS1 from this picture. So your design would not include P3 in the allow list or in the provider, the block list, naturally. But however, the algorithm would admit if from AS2, so packet comes in with source address in P3, it would be admitted. That seems like a fundamental flaw in the design.
Yeah, and in this figure, we assume only AS4 perform the self-filtering. So we focus on ingress self-filtering on AS4, and we assume other ASs do not deploy self. So yeah, we can improve the design accordingly.
Yeah, that doesn't answer my question. AS4 is performing SAV, but basically
Yes.
it does not have P3 in its deny list or in the allow list. But your algorithm says that if it's in neither of those, you would still accept the packet with an address in P3, and that seems like a fundamental flaw to me.
Yeah, maybe that's why we also need a allow list. We can not.
No, you can have both. I mean, the way you designed allow list and deny list, you have both. Even though you have both those lists, fundamentally, like P3 is admitted when it should not be admitted if the packet is coming on from AS2 to AS4.
Yeah. Sharon, it's Ben here. I think I agree with you. I think you're right. And I think the flaw is that this procedure works fairly well to generate egress filters from AS4, but not per interface ingress filters into AS4. Because that would be the correct behavior on egress from AS4, right? Just not on ingress from AS2 to AS4.
Okay. Yeah, I will also present this solution in next session later. So maybe we can have a deep talk about how to adjust the design.
Okay, thank you.
I'm from Huawei Technology. Thanks for your presentation. Some of my comments overlapped with Ben's comments. Maybe some corner scenarios should be considered. For example, the Wiley path scenarios, although there is a small portion of such cases, but you may mention that in the draft. If you have that, that would be okay. And I have another question that will this method introduce too much overhead on the data plane on AS4 routers, because we may have a very big provider call. I mean data plane overhead.
Yeah, but I think I should do some measurement research. I should compare the size between provider coin and customer coin, right?
Yeah. Okay.
Okay, thank you. Okay, thank you. 我觉得时间缩短点了，来不及了。
Okay, I'm going to introduce our design of the signed Savnet peering information object for deploying inter-domain Savnet. I'm Li Chen. I'm presenting on behalf of my co-authors. So the background for inter-domain Savnet is as follows. So the attacks based on source address spoofing still present significant challenges to internet security. And to mitigate these attacks, we need SAF. And there's already existing solutions, but they all suffer from validation accuracy and operational overhead issues. So in this working group, we are proposing the Savnet protocols so that the SAF-specific information can be exchanged between the ASs. And in the last Ietf meeting, we have presented our emulation study to show that our proposal can achieve higher validation accuracy and lower operational overhead in the large-scale scenarios. So yeah, in the interest of time, I would not go into the details of how Savnet protocol works. But here I only want to mention that the problem that we're trying to tackle is actually in the first step of this example on the right, which is how AS1 and AS4 set up a Savnet connection. And this actually brings us into the problem statement that, of this draft. So the key issue with the inter-domain subnet for operators is incremental deployment, and this is the statement is like this. So the protocol speaking agents, so they need to find and establish connections with other subnet agents. So currently we are assuming that the peering is done purely manually, and this is cognitively and operationally expensive, and there's a learning curve for the operators. And more importantly, there's no turnkey benefits for the operators, and the subnet peering must be negotiated one by one. So there's actually no incentive for newly adopting ASs. There are two potential solutions for automatically establishing subnet peering. The first one is the gossiping and flooding protocols. And we all know that it will be bandwidth and computationally expensive. And our proposal here is that we want to have a public registry that contains all the ASs which both deploy subnet and are willing to set up subnet peering relationships, so that a newly adopting AS can use this registry as a reference and pick an appropriate ASs to set up subnet peering. We believe that RPI may be the most suitable choice for this registry because it's already playing a central role in routing security, and source address validation is a key part of routing security. So let's go into the details of the SysP object. We are proposing a new content type, and we intend to register this number through IANA. And this object will contain two important information. The first one is the AS ID, which contains the AS number of that of the AS that have deployed and want to establish subnet connections. And the second one is the IP address of the subnet agent within that AS. So to validate a SysP object, the reliant party must perform all the validation checks as specified in RC 6488, as well as the following additional specific validation steps, including the AS identifier delegation extension, the EE certificates AS identifier delegation extension, and the IP address delegation extension. That one must be absent. So a router can use a AS path from BGP announcements, ASPA objects, and SysP to actually find the closest or the most appropriate ASs to set up some subnet peering. A potential procedure can look like this. So it can first identify the closest AS using the ASPA object and the AS path information. And then the SysP object can be utilized to determine which of the ASs have already have deployed the subnet. And finally, you can set up, you can select the candidate peering ASs. And the selection criteria might include multiple factors, including existing peering policies, traffic volumes, or existing peering agreements. And I think that's it. And thank you. And I would like to see if there's any comments.
Yanfei, okay.
That is Yangfei Guo from Zhongguancun Laboratory. Could you please flip to page 5?
Page 5. This one?
Previous.
Yeah. Down.
5.
这是第几页？
第4。
The next page.
Okay.
Yeah. Which version is the address is IPv4, IPv6, or
Yeah.
I think it
Right.
you may define the address family.
Sure. Yeah.
And if the address field is a single address, or in my opinion, sorry, I haven't read the draft, but I think it may be a list of address.
Yeah. That's possible. Yeah.
Yeah, that's my suggestion.
Right. Thank you.
Ben.
Ben Work Online. So I had similar thoughts about the profile, but I know that you're presenting on that later today at CyderOps, so maybe we can talk about the profile in more detail then. My main question was, I haven't seen anywhere any work on describing what the kind of minimal set of peers that one needs to have in order to make sure that you're receiving the necessary amount of information for the protocol itself to operate. The peer kind of selection algorithm that you map out in the draft is a bit hand wavy. It doesn't really it doesn't really describe kind of, given this peering topology in BGP, this is the minimum set of SAV neighbors that you need to be exchanging information with in order to make sure that you've got sufficient information to perform the filtering correctly. Is that documented somewhere, or is that work still in progress?
We intend to add it in the next iteration, and definitely the appropriate amount of information needed for the newly adopting AS is something worth studying, I think, using simulations or emulations. Yeah. I don't have an answer right now.
Just one more observation to think about more than anything else at this stage.
Sure.
Is in the kind of the description of kind of discovering appropriate ASs to peer with. You seem to be interpreting ASPers as bidirectional, as in kind of inferring a customer to provider and a provider to customer relationship. That's not necessarily wrong.
Right.
But it's worth thinking about the fact that an ASPer does imply that kind of bidirectional relationship from a routing perspective, but it's not necessarily a perfect mirror image with the way that relationship works with source address filtering.
Yeah, I see. Yeah.
So I think it's something to at least describe. Like if you think that relationship is congruent in the two cases, then I think it's worth writing down why you think it's the case, because it's not obvious to me.
Yeah, sure. We'll make it clear in the next iteration. Yeah.
Okay, thank you.
Okay, hello everyone. Okay, SJ from ZTE. I'm going to present the BGP operations for inter-domain SAM.
Sorry.
Okay. This document introduces BGP validation mechanism to filter invalid address and mitigate traffic spoofing. It attempts to collect and present some operational and security considerations to deploy SAM on routers in inter-domain networks. It is proposed at October 2023 and has been presented at Ietf 118 meeting. And in this current revision, we have updated, includes the comments to address comments received from Gaofang, and added scalability considerations, and the co-author updates and some editorial changes. Here's a use case. This use case shows an example for a traditional fast transport network. And from this figure, we can find the traffic track from customer to operator, and also includes the opposite direction from operator network to the customer. The routing security tag may include the route leaks, route prefix hijacking, and the source address spoofing. In this draft, we're mainly concerned about the, filter location at G plane between which may be used or connected between the different operators. As network will involve the inter-domain AS network. And for the validation policy, to address the, the route leaks and the route prefix hijacking is out of the scope of this draft. And in this draft, we only, to address the source address spoofing. And the assumption for this cell validation, the source address prefix is trusted. So the only question for this draft is to address the incoming interface accuracy. The solution for for the cell intra-domain networks is to solve the security requirement. This requirement is to support the ability to validate the accuracy of incoming interface. And for the validation mechanism, we use the POI mechanism policy. This policy involves, first is to tag the root prefix. And the second one is to bind the interface with POI and generate the prefix and interface policy. And then, it can be generated the involved or corresponding extended prefix table. And when the traffic is received and routers, the router can use this policy and apply this policy to validate the traffic incoming. We also have some, provide some scalability consideration. For the scalability, this draft provides these types of policy. It can be used per AS level, community level, and router level, and prefix level. And this draft also provides some operational consideration. For the BGP validation mechanism, it should support validation at the edge or border routers and should support backward compatibility, should be hardware friendly, and should comply with the router's existing policies and should support network implement requirement. For the next steps for this draft, we would like as feedbacks from the WG, and our main feedback is about whether the considerations for this BGP validation mechanism is in right way. The assumption is that the BGP root prefix is trusted as an assumption. And the only question is to address the incoming interface is the right interface. Okay, thank you.
So if there are no questions, we will continue the next presentation. Okay. Okay, thank you.
Good afternoon, everyone. I'm Nangong from Huawei Technology. The topic of my presentation is BGP extensions for source address validation networks, that is BGP Savnet. We have many discussions on the topic of problem statements and use cases, and the BGP Savnet also follows the previous the analysis and the drafts. In this draft, we propose to extend the BGP protocol to advertise site-specific information, which has already mentioned in the intra-domain and the inter-domain architecture drafts. With the advertise the site-specific information, edge or border routers can generate more accurate site rules. Existing site mechanisms mainly rely on local routing information, but now we propose to use both local routing information and site-specific information. BP Savnet can be used for protecting internal prefixes. Here, internal prefixes means the source prefixes belonging to the local customer networks. In this figure, we can deploy BP Savnet on edge routers connected to our customer networks. That is router 1 and router 2, two edge routers. With extended BGP messages, they can exchange some asymmetrically advertised rules. Here is P1 and P2. With the advertised rules, R1 and R2 can build a complete source prefix list at the interface connected to the customer network, so improper block problems can be avoided. BP Savnet can also be deployed on the border routers, that is router 3 and router 4, that are connected to other ASs. It can also be used to block the spoofed source addresses coming from other ASs. In this example, edge routers, router 1 and router 2 can automatically advertise internal prefixes to the border routers. When router 3 and router 4 receive the advertised internal prefixes, they will build a block list at the external interfaces connected to the other ASs. So any packets with internal prefixes will be blocked at router 3 and router 4. The proposed solution can also be used for protecting internal prefixes with good deployability and convergence. In the example, we can the solution can work well when we only upgrade part of routers. That is router 1 and router 3 in this example. Router 1 can advertise the internal prefixes to router 3, and router 3 can also build its block list at the external interfaces. So in the under the condition that R2 and R4 do not deploy BP Savnet. So this method supports incremental deployment. And for the convergence considerations, the BGP messages have the similar propagation speed to the route speed, propagation speed. And the convergence of each router doesn't depend on the convergence of other routers. Each router can converge independently after upon receiving the advertised messages. The solution can also be used for protecting remote prefixes besides the internal prefixes. Here, in the example, we deploy the solution on AS1 and AS4. And in the example, AS4 will conduct a source address validation. So we named it as validation AS. And AS1 is named as source AS. It means the prefix of AS1 will be protected. So in this example, AS1 will advertise the target source prefixes to the AS4 and also the expected incoming interfaces of the target source prefixes. And AS4 will generate corresponding sub rules. We also the solution also support good incremental deployment, and we also give some convergence descriptions in this draft. And for the security, we have received some comments from some people, and we consider that we can protect the source address by conducting ROA at the validation AS, or we can the validation AS can also directly get the target source prefixes from the RPKI data, and the BP session can be protected by using TLS. Okay, today this is the first time to introduce the BP Savnet in Savnet working group. So comments are welcome. Thank you.
Okay, we must take the discussion offline. So the last presentation.
Okay, I'm Chang Wanlin from Nutri Technology. I will behave my co-authors to present this draft. The Savnet YAM model provides a base framework for configuring and managing and service subsystem, include server table and server rules. The data models is decided by referring the Savnet functions defined in relative drafts. The Savnet YAM is an interface between management plane and device plane. The Savnet YAM consists of three functions: configuration, state, and event report. The Clark version update according to the Savnet deployment experience over the last 7 months. Firstly, the update 1, we update for general configuration. Firstly, we add entries load number, capacities, a line of entry server rules. Secondly, enable the function of reporting top subrules hit by spooling packets. Thirdly, enable function of collecting Savnet blocking flow information. Update 2 for interface configuration. Firstly, we enable the function of reporting the top server rules hit by spooling packet to specific interface. Second, enable the function of collecting the Savnet blocking flow information on specific interface. Update 3 for static server rules configuration. First, we add a load number for a line of static server rule capacity. Second, we add the check type for supporting static server rules of block list mode. Update 4 for server table status. First, we add the total packet static for calculating past packet amount and troubleshooting. Second, we support for showing the flow information of Savnet blocking packets. Update 5 for Savnet interface data. We add the total packet static on specific interface for maintenance and troubleshooting. Finally, for Savnet event report, we add the report the information of the top N server rules hit by spooling packets. We required for more review and comments. That's all. Thank you.
Okay. I think this work is far earlier for our current status, so we can have enough time to improve it. So, so thank you for all of you to come here to attend the Ietf meeting. So let's meet the next in one core. Thanks.